In lesson 11.3, we're going to do some indirect measuring with similar triangles. Using similar triangles can be really helpful if we're trying to find the height of an object that might not be possible to measure by hand. So what we could do, just for example, as you look at the diagram down below, is we could measure the height of a flagpole perhaps, and what we could do is we could take a mirror and put it on the ground in between you and the flagpole. So here's your mirror down here where the green highlight is. And then you walk backwards until you can see the top of the flag in the mirror. So what you find out then is that the two angles next to the mirror are equal. Or in other words, the angle that's right here is equal to the angle right here. In addition to that, we also know that we have right angles, like the right angle between the person standing and the ground, and the right angle between the flagpole and the ground. Hence, we know by angle-angle similarity that we have similar triangles. In other words, the triangle on the left and the triangle on the right are similar. Well, that tells us then that each of the sides are in proportion, or in other words, they have to have the same ratio. So what that tells me is that I could write down a proportion in order to solve this. For example, if I ignore what's up on the board right now and I do it the way that we were talking about before, we talked about how the 6 from my height, for example, should compare to the x from the flagpole's height. So I would have written down 6 comparing to x, left to right. And then I would also compare the distance from me to the mirror, which would be 10, as compared to the distance from the mirror to the flagpole, 35. So I would have set this up as 10 over 35. These are the ways that in the previous examples they were set up. And I'll talk about what's up on the board as well, and just a little bit that was typed in there. But this is the setup. And that's because when we know that we have similar triangles, that my sides would have to have the same ratios, from the left to the right, left to the right. Now we do the cross multiplying, and in case you don't recall, that means I'm going to multiply the 6 times the 35, and I'm also going to multiply the x times the 10. When I multiply the 6 times the 35, that's 210. So I write that down. I have my 210. And that's going to be equal to my 10 times my x, which I call 10x. So the 10x is here from the cross multiplying, and the 210 is from the yellow being multiplied. And then when I divide both sides by the 10, I end up with 21 as my answer. So x equals 21, and my label would be in feet, and that's representing the flagpole height. Now let me call your attention to the setup that was typed in before I started doing this by hand, and you'll see that it says 6 over 10 and x over 35. So one of the other things that similarity tells us is that the ratios within the triangle should match up as well as across triangles. So what I said with you guys is that the left side of the left triangle, the height of me on the left compared to the height of the flagpole match up. That was the 6 over x, and that should be the same as the height from me to the mirror and the mirror to the flagpole matching up. But what I could have said instead is my height, 6, compared to my distance from the mirror, 10, should be the same ratio as the height of the flagpole, x, compared to the distance to the mirror, 35. And what I'm talking about is I could have used, instead of what we just did together, I could have used this ratio set up for a proportion highlighted in purple. It's not going to matter, it yields the same answer. So you can work within the triangle and then compare to the other within the triangle, or across triangle and across triangle. Either way is just fine. Another example here, just to kind of carry on through with our understanding of similar triangles, is that if I know that these two triangles are similar, we could talk about suns and shadows. So we'll notice that we have a 5'5" person casting a 7-foot shadow, and now we have a light pole casting a 20-foot shadow, and I want to know tall that shadow is. So what I do is I look at the comparisons. So I take the 5.5, which is the height of the person, and I can compare that, as earlier, to the height of the pole. That's this comparison for a ratio. And then I can say that that should be, if I know that these triangles are similar, the same comparison as my 7-foot shadow to the flagpole, or not flagpole, the light pole's 20-foot shadow. And here's that comparison for ratios. We set those two equal to each other because we know that to be true in two similar triangles. And then we use that cross-multiplying technique again. We're going to multiply the 7 times the x, which is, in other words, 7x. And we're going to multiply the 5.5 times the 20, which is the same thing as 110. And so now you're looking at, you have your 7x equal to 110. Divide both sides by 7, and you find out that that light pole is 15.71 feet tall. That's your x. So again, once you know that two triangles are similar, set up the ratios equal to each other, cross multiply, and then divide.